All right, welcome back. And now we're going to talk about mobile UI security, where UI stands for user interface. This has been one of my favorite research topics in the last few years. So I think there is a lot of interesting material to cover. So let's get to it. So I would like to introduce a term they call UI feedback loop. And this is to show the importance of the user interface and why it's important security wise. On the left side, we have a telephone, and then on the right side, we have the user. And the user interface used as an output channel is a way for an application or for the operating system to communicate something to the user, but it's also used as an input channel to, for example, get some input from the user, like keys, username, password, messages, and things like this. And somehow, an attacker that is able to hijack this kind of a feedback loop, this kind of output channel and input channel, well, it might be able to know what is currently displayed to the user. It might be able to modify what the user sees. And on the input side, it might be able to know what the user is clicking on, and it might be able to inject user input. And if an attacker is actually able to hijack this loop, then bad things can happen. And this is what these slides are about. Okay, so question is, how is it possible that an attacker can actually hijack this feedback loop? What are the techniques? And two, if an attacker can do this, what are the repercussions? And before I start with the material, there is a bit of a disclaimer, in a sense that for a long time, this kind of research has been dubbed like more academic side, in a sense, it's just a UI bug. I strongly believe this UI security things is actually important, and it goes beyond the academic realm. And the reason is the following. Uh, Android features a lot of low-level security mechanisms, and in the last 10 years, there have been a lot of improvements from sandboxes, permissions, exploit mitigation techniques, attack surface reduction, and things like this. And a few years ago, there was a talk from, at that point it was Nick, at that point was the head of, I think, Android security. It was an interesting talk on all the efforts of the Android security team, and it is actually great effort and great work. But turns out that some bugs of the user interface can actually bypass all these low-level mechanisms. And so in this set of slides, I'm going to try to convince you that these attacks actually matter. So I have two categories of attacks that I want to show you. The first one is phishing, and the second one is clickjacking. Phishing, we already touched a bit on this. In phishing, an attacker lures the user to insert their credentials somewhere. So it could be credentials, username and password, it could be the credit card information, and things like this. And again, the idea is that the attacker wants to trick the user to insert these credentials somewhere that is under control of the attacker, so that the attacker now learns what the username and password is, for example, for your Gmail account. And clickjacking is different, and that's a term that maybe you're already familiar with, maybe from the web. The idea is that the user clicks somewhere, but the attacker tries to convince the user to click somewhere that is security sensitive, of that by clicking at a specific place, the attacker gains some advantage. Okay. If you don't know about clickjacking, great. If you know about clickjacking from the web world, please pay attention, because the concept is similar. Like, you want to have the user clicking somewhere, and the idea is that you steal the user click, or the click goes somewhere where it's not supposed to be, but the implementation is completely different. Okay, so the way it works is actually very different. So if you have previous knowledge on this, keep in mind that this previous knowledge may not really apply in the realm of mobile security. Now, let's talk about mobile phishing, the first one. So the threat model for this attack usually is the local attacker, where basically the attacker already has a malicious app installed on the system. Of course, you can have mobile phishing that is not using this threat model, but is more, the user receives an email, and this email contains a link, and then you go to the link, and then this page looks like Google, and then you put username and password there. Of course, this kind of more traditional phishing attack you will see in the web still exists, and is still relevant for mobile phishing. What I want to talk about in these slides is phishing about specific, the application components, not just a website. Okay, so for what concerns the website, it's similar to the web phishing. Again, here I want to talk about mobile phishing affecting Android apps. Okay, so the goal, as we said, is for an attacker to try to steal the victim's sensitive information, and the basic technique is to spoof the user interface of a legitimate website of app. For example, in terms of an application, you are familiar with a Facebook app, and maybe the goal of an attacker would be to create an application whose user interface shows up looking like the Facebook app where he asks you username and password. Okay, and again, these are common examples of what the attacker may try to steal. Phishing goes under the bucket of social engineering attack, in the sense that to succeed, phishing attacks needs to somehow convince a user, a human, and to convince a human, there are some non-technical factors that actually become important. In a sense that it's not completely automated. You need to really interact with the user, and you need to fool the user. And to fool the user, or to be more effective in fooling the user, again, there may be some non-technical aspects to keep into account. For example, the first one is the timing. Is the user expecting these questions? Is the user expecting to provide username and password? If yes, well, maybe it's more likely the user is going to fall for it. If no, then maybe he's going to be surprised, and then maybe he's going to be suspicious about, oh, why is this app asking me for this? And again, if the user feels something is weird, then the attack is likely to fail, or more likely to fail. Okay, so there are many variations of phishing attacks, and these variations are usually aiming at making the attack more believable. So the key problem on mobile is the following, that makes these attacks powerful. That, let's say you have this user interface. Is this a real Facebook app? It's tricky to know, and in general case, it's not possible to know by just looking at this user interface. On the mobile web, on the web platform, on a web browser, when we visit web pages, there is actually a technical way to understand whether you are actually talking to the real Facebook web page. For example, we humans know that the real Facebook page is facebook.com, and through the green lock, or now the lock or HTTPS, we know that we're actually talking to facebook.com. Okay, so of course, if the user is not paying very attention, and so maybe it's not facebook.com, is Facebook, maybe with the zeros.com, then of course the attacker still works. But if the user is very careful and checks really in detail the domain name that is interacting with, then he can figure out, okay, this is the real Facebook, or this is not the real Facebook. On the mobile interface, instead, you don't have this. There is no place on the mobile app that tells you, yes, this is the real Facebook application. Okay, so that's why this stuff is tricky, and that's why it's difficult to protect yourself from phishing attacks. Of course, it's more complicated to pull off in terms of the assumptions that we have. Again, remember, the threat model for these attacks is that we have an app already installed. The attacker has an app already installed on the user's phone. So once this assumption is satisfied, then let's say it's much easier to pull out these attacks. On the other side, maybe it's more difficult to pull out phishing attacks on the web, like with domain names, but the assumptions are easier to satisfy, in the sense that you just need to send an email to somebody, maybe with some link that looks like Facebook, and it's much easier to convince somebody to click on a link than to install a malicious app. Okay, so there is a kind of a trade-off. So don't think that this attack is, oh my god, we're all doomed. No, this attack still relies on the user installing a malicious app. But we are researchers. We want to find what the current problems are, and so that we can fix things in all the various scenarios. So that's why this stuff is relevant. All right, so in terms of phishing, the usual attack works like this. The user clicks on the Facebook icon, and this could be really the real Facebook icon, and then somehow the malicious app in the background tries to understand whether the user just clicked on this. So the idea is that you have a malicious app in the background that tries to read information, and there were a number of APIs, a number of tricks, like the proc system or get running task APIs and so forth. And an attacker could use this information to infer, the user just clicked on the Facebook icon. And the idea would be that when the attacker understands this, then it would pop up with an activity that would look like the Facebook activity. Okay. But so now you understand why getting the timing right is important. If this Facebook UI would pop up, out of the blue, then maybe the user, it's suspicious about this. But if this UI appears just after I clicked on the real Facebook icon, then you get this right. I mean, it's tricky for a user to not fall for it, because you could be, Facebook just de-authenticate myself, or I got logged out. Let me insert my username and password again. Okay, so these attacks are quite effective. Turns out that these things were have been known by the community since a while, or some papers on this topic, and Google took note about this and somehow with time fixed several of these potential for inferring information about the state of the system. Okay, so for example, these three examples that I have here, in the latest version of Android, they don't work anymore. And this brought me to, bring us to, how can an attacker do this stuff without these things? So first of all, there are two things. One is that people figure out other things, other ways that we're going to explore now. The second one is that this step is not strictly required because you can have other tricks. For example, you can create a shortcut that looks like the Facebook one. So maybe the user clicks on an icon that looks like Facebook, but is not really Facebook. And at this point, if the user is fooled to believe that the icon is actually the Facebook one, then it would not be surprised when he sees a Facebook login prompt. Same for a notification. One could create a fake notification or a notification that fakes to be some notification from Facebook saying, oh, this person that you really liked, he actually wrote you a message. Why don't you click on here? Then you click on it, excited to see what this person wrote to you, and then they pop up with, oh, please put your username and password, kicks in. And again, the user may fall for it, okay? So usually, if you don't have such channels, it's not the end of the world, but of course, such channels help a lot because they help you stay under the radar. And this brings me to the topic of mobile password managers. We discussed about these password managers in a previous class. And mobile password managers can be or could be tricked into thinking that a specific application was the real Facebook application. And when abusing this password manager, basically we would have you have a malicious Facebook UI with the autofill prompt of a password manager popping out. And again, this is not the password manager would give automatically username and password, but it would add legitimacy to the attack of the attacker. Okay. And again, for example, this would be a fake UI. And then if you see something like, oh, do you want to insert your username and password related to Facebook from LastPass or from another password manager, then you would, it's more likely that you fall for this attack. Okay. And again, one thing we explored already is how to abuse Instant Tab, where basically a user would be able to try apps with one click, and some part of the app would be stored on the device. And this part of the device, even if it's not a completely installed application, will still have a full control of the UI, and you can pull off these UI attacks. Okay, so there are pros and cons. The one aspect is that, again, you are assuming a local attacker, and it's more tricky to have a local attacker with respect to a remote attacker. Sorry, this is there are pros and cons about this mobile phishing. I think the pros and cons here about pros and cons about these instant tabs. These instant tabs, it's a pro. There is a pro in the sense that by clicking a link, you are able to go from the link perspective to having code execution on the device. So somehow you're able to bring yourself from local attacker to remote attacker. It's less practical because 2 additional clicks are required. Okay, and the user may be tipped off by the install instant tab prompt, but the attacker could make it very realistic. But it's one of these pros and cons to keep in mind. But maybe you could argue that 2 additional clicks and this install instant tab prompt, it's less suspicious than it's let's say it's easier to achieve with respect to having the user installing a malicious app. Okay, so you could argue this. Okay, for instant apps, again, I think we checked this in the past, but the idea is that, you know, in modern version of Android, you have a possibility to let the user install a sub part of your application. And this is used, for example, in games, where you go on the Play Store and you can say something like try now button. And if you click on the try now button, then a part of this application will be installed on the phone. And then I mentioned this already in the past, where basically you could link instant app to links. So in a way that if you go to a specific URL, then you can trigger a prompt for installation of an instant app. And if the user does open up, then this will trigger, you know, the installation of the instant app. And again, the attacker now goes back to having full control of over the UI. And last slide on this topic, that I think I discussed this already in the past, but, you know, for completeness, to have this slide self-contained, I want to repeat here. If you have this instant app trick, then you can pull off an attack like this one, where basically you go to a web page that, again, this web page could be unrelated to, you know, some web page where you need to pay something, and then basically the user will click on the, you know, click on PayPal. Great. Now this would activate something like, you know, do you want to install this instant app? And again, here there is a white square, but maybe, you know, this is a white square because we uploaded an app to the Play Store with a white square. That's under control of the attacker. We could put anything we wanted. Once the user says yes, the instant app is installed, and at this point we would have our own fake PayPal UI with also tricking, in this case was LastPass, in suggesting, hey, do you want to fill your username and password associated to PayPal? Okay, and attack is completed. And again, this attack did not start with an app installed on the system. So somehow the instant app allows us to start from a link and to lure the user to fall for it without requiring him to install a proper app, a proper malicious app from the beginning. So somehow we remove some of the assumptions from these attacks. And again, this was our malicious app, not the real PayPal app. Cool. And here there are a couple of papers that are relevant for this topic. The first one is a paper with some of my co-authors from UCSB, where basically we explored you know, all these problems in terms of trying to understand, you know, given a UI, how can I know which app is that? So we explored this confusion, let's say. This other paper about phishing attacks on modern Android was about the mobile password managers or the instant apps, and how to abuse these features to create more phishing attacks. And there is actually a third paper that that a student of mine just published. I'm going to put the link, you know, in a couple of weeks when the paper is going to be out. That is about how to automatically find these side channels or these APIs that may leak the state of the application of the phone automatically. So at the beginning, I mentioned this. I think it was a get running task API or profile system API. All this stuff is fixed. Again, these are APIs that are used by an attacker to understand which app is currently running, which app the user did just start, and so forth. And again, with the student of mine, we did a project where basically we built a system to somehow scan automatically all the Android APIs and try to understand whether each API could, or which API could be used to infer the state of the system. Okay. Again, I'm going to add the link when the paper is published for completeness. Cool. All right. So there was a, you know, some kind of a brief overview about phishing attacks. You know, we already discussed about these phishing attacks in the past. Phishing is kind of a known thing in the web. And I would like to spend a bit more time now on the second part, which is click checking, which maybe some of you already know from the web part, but you know, if you don't know about this, okay. If we know about this, keep in mind the technique is actually different, okay? So keep this in mind. All right, this is one of my favorite topics, so eyes out and let's get to it. So the goal for an attacker in a click checking attack is to substantially steal a user click. Okay, so rephrase, we want to convince the user to click on a button or a place, and conceptually, the problem is that the click's actual semantic is very different than what the user thinks. So somehow the user needs to click somewhere, and the user thinks, okay, I clicked on button X, and button X has semantic, this specific semantic. I'm gonna, send a message to somebody, something. But what actually happening, or what this click is actually enabling, is something very different and much more powerful. And somehow this attack is done in a way that somehow the attacker gains some advantage. Okay. These attacks are known in the literature also as overlay attacks. So if you want to know more about this, of course, you can always write to me. If you want to Google for it, you can Google for clickhacking attacks on Android, or also overlay attacks. Okay, so overlay attacks is also a term that is quite used. Why overlay attacks? Well, because these clickhacking attacks, as we see, are sometimes built by creating a number of overlays, and so to confuse the user. Again, we're going to see what this means in a second. All right, so before we discuss the attacks, I want to discuss a couple of permissions that are very relevant and that somehow enable many of these attacks. Okay, so the first permission is something called system alert window, that I informally call draw on top. I think I mentioned this in the past, but the idea is that if an application has this permission, this app can draw arbitrary windows and overlays on top of the screen. And this can be done even if the app is in the background, so you don't need to interact with it. If you interact with an app, the app, of course, can draw everything it wants on the screen. So no big deal, you don't need this permission. This permission is useful when an app wants to do this from the background. So in the background, then with this permission, you can draw anything you want on the screen. And these overlays can be completely custom. You can customize the shape, you can customize the content, so how to draw each pixel. You can customize the transparency, so you can have something that is semi-transparent or completely invisible. And you can also set up how this overlay reacts to clicks. And in general, it could be clickable or pass-through. What does it mean? Clickable means that if you have an overlay and it's clickable, it means that once the user clicks on it, then the click is captured by overlay. So the app generating this overlay is notified about the click, and it knows where the user clicked, okay? But this click is not going to be propagated below. So for example, if you have an application here and then the malicious app creates an overlay here, and the user clicks on this overlay, again, the attacker knows where the user clicked, and the attacker knows where and when the user clicked, but this click is not propagated down. So this click is not going to be reaching the application on the bottom. Okay. The alternative is that you set up this overlay as pass-through. What it means is that once you click on it, basically the click goes through this overlay and reaches what's on the bottom, but this overlay basically is not going to be notified when the user clicked and where the user clicked. Okay, so you don't know where the user clicked. Cool. This permission is used quite often. These are the numbers from 3 years ago. So it was about 10% of the apps that we could find, among the top applications. And it was used by, or I think it's used also now by big apps like Facebook, Skype, and so forth. Okay, so it's very difficult for Google to just remove it. But my understanding is that in the years there are plans to deprecate this. I don't think we are there yet, but I hope that this work or many other works on this topic somehow motivate Google to move on and somehow deprecate this permission. And now I want to explain how clickjacking works. Again, this attack I'm going to show is not from me. It's been developed in the past by other researchers. But that's the first clickjacking. The simplest version of clickjacking. It works in this way. Let's say you have an attacker that wants to convince the user to click on this OK button. Okay. And the idea is that once the user clicks on this OK button, then the attacker is gonna, in this case, is gonna have access to a accessibility service with which you can do a lot of damage. Okay. Again, I already said this in the past, something about accessibility service, but I have some slides on this later on. But believe me that if an attacker gets access to accessibility service, it's game over. He can do basically whatever he wants. He can read off things on the screen. He can automatically inject clicks, and you can do many bad stuff. And again, I have some videos later on this topic. So let's say that, again, the attacker wants the user to click on OK. Now, if the user maybe reads carefully what's on the screen, maybe will never say OK to this. And that's where the click-jacking attack kicks in. In a click-jacking attack, the attacker would do something like this. It would basically, goal is to have the user clicking on the OK. The attacker will basically draw an overlay on top of this, covering everything. And then he would also draw, some button, but he would set up this button in a way that once the user clicks here, the click actually, pass through the overlay and actually reaches the bottom and reaches the OK, and the attacker wins. Okay. I think this attack was disclosed for the first time in this Black Hat Asia talk. Check it out, and was very, very interesting. Now, this attack was known, has been discovered in 2014, and Google moved on and tried to protect from this. And the main protection that they had was the obscure flag protection. Again, obscure flag is a protection against rejecting, and Google introduced this obscure flag, and it works in this way. Basically, when the user clicks on a widget, the widget could be like a button. Then, so in this case, it would be the OK button or the CBD service settings. When the user clicks on this widget, basically there is a flag that could be set. The flag is called flag window is obscured. This flag is set if and only if there was an overlay covering the receiving widget. So basically, if in a normal situation you have the OK button and there is not covered by anything. So once the user click on this, the button is going to receive there was a click event, and the flag windows obscure is not going to be set. And the idea is that the application can actually check this flag and decide on this, okay, the flag windows obscure is not set, which means there was no overlay on top, which means everything should be fine, right? Instead, if under this attack, if there was something on top of this, then the user clicks, the click reaches the OK button, but the in the event, the on-click event for this OK button, for this OK click, the flag windows obscure would actually be set. And so the application could check, oh, wait a second, the flag windows obscure is set, something is weird, I'm not going to trust this click, and it's going to reject the click. Okay. Alternatively, I think there is an API called set filter touches when obscure, but I think the way it works is the same. There is this kind of flag, and if this flag is set, you refuse the click. If it's not set, then you assume the click is trusted. And I want to show how the CVD service settings was modified to use this obscure flag protection system. So a new version of Android, if you have settings like this, and let's say we draw something on top, so we draw an overlay on top. For this view, it's drawn semi-transparently so that I can show you what's going on the bottom. During an attack, of course, the attacker would draw this completely opaque. But let's say we draw an overlay, and let's say the attacker, the user clicks on this OK button. Now there will be a pop-up that you can see here. And zooming in, this pop-up will say, because an app is obscuring a permission request, settings cannot verify your response. So this is the obscure flag in action, where basically the settings app, which is the one that displays the CBD service menu where the user can click on the OK, basically says, the obscure flag is set. I cannot trust this click. And so it says, I cannot verify your response. Okay. And so the click doesn't work and you cannot do, the attacker doesn't win. So at this point, basically this obscure flag is, was the main and only way for the settings app to protect itself. And it was considered somehow secure, but then, that was one of my main research projects during my PhD, and I found a way to bypass it. So how does it work? Somehow the obscure flag is helpful to detect that another overlay is on top. Okay, that's what the obscure flag does for you. But who says that you need to cover the target OK button to somehow pull off a click-jacking attack? Okay, so that was the intuition. So if I can somehow do the attack in a way that I don't need to cover the OK button, then maybe I still win. Maybe the obscure flag is not going to be set, and maybe the receiving application is not going to be alerted that maybe something is on top. And so the idea was the following. What about, instead of covering everything, I basically cover everything except the OK button. And then the only thing I need to find is some excuse for the user to actually click on the OK button. So I could do something like this, okay? So in this way, basically everything is covered, but not the OK button. So when the user is clicking on the OK button, technically there is no overlay on top of the OK button. And so the obscure flag is not going to be set and the target application is not going to notice any attack. And this attack actually worked. And I called it the context hiding attack, where basically the OK button, you see it, but you're missing the context. You're missing what kind of stuff you're authorizing. And that's, again, what makes this attack quite powerful. And yeah, it was a bypass for the obscure flag. So it was tricky to fix this because it's a design shortcoming. It's not just like a buffer overflow. The idea is that apps do not have access to enough information to understand what's going on. And I believe this obscure flag is conceptually broken. And again, it's difficult to fix because if you would tell the application, the target application, the full context of what's going on, maybe this application could defend itself because now it says, oh, there is a lot of drone on top, so I'm not going to do anything. But maybe this mechanism could be abused by an attacker to do state inference attack and know what more or less was going on and maybe mount phishing attacks. Okay, so it's quite difficult. So somehow, what Google did to fix this bug is that for these special apps, for example, like the settings, what they do is that they automatically remove all the overlays, no matter what, and so the user is going to notice everything. But we're going to show later how this fix could work for the settings app, but it's difficult to apply for the third-party applications. Another variant of clickhacking that I focused on was this context-aware clickhacking. So consider the scenario in which you don't only need to steal one click, you need to steal maybe 2 or 3 clicks from the user, okay? And I call this multi-stage clickhacking, when we need to steal click number 1 and then click number 2. And you need to answer a bunch of questions to pull these attacks off. For example, when to transition to the next stage. The user clicks on the fake button number 1, but then somehow the attacker needs to know that the user clicked there so that he can modify the overviews so that the user is pushed to click on the fake button number 2. And then you also need to account for mistakes, like what if the user didn't click on button number 1, or what if the user clicked on the button number 1 but after a while, so you need to get the timing right and so forth. So it's quite tricky, and there are security mechanisms again that somehow limit the information you have about these clicks if the click doesn't reach you. As I mentioned before, you can set up this overlay so that if the overlay is clickable, which means that the click is reaching the overlay, and in this case you know everything, but the click doesn't go through, and that's not what we want for clickhacking. We want to set up overlay so that once you click on something, the click goes through. Okay. So it's tricky. Or in the case of context hiding, we want to set up overlay so that we cover everything except the button. So the user is going to click on this hole. But if the user clicks on the hole, it doesn't click on us. And if it doesn't click on us, we don't know where the user clicked. So there are these problems. And in general, if the user doesn't click on something belonging to the application, the malicious app is not notified about the user click. And there is another security mechanism, which is this flag watch outside touch. Basically, you can create an overlay with this flag. And basically what you're saying is that you want to be notified about clicks, also if they're not touching this overlay, if they're touching somewhere else. So you can do this. You can create an overlay so that the overlay is here, and if the user clicks here, you still get notified. But for security reasons, you don't get the coordinates. You only get 0, 0. Okay. So basically, the user clicks here. Sure, you know that the user clicked outside your overlay, but you don't know where the user clicked. Again, it could be a problem. And again, intuition here on how to build these context-aware click checking attacks and how to figure out where the user clicked, when he clicked, when transitioned to the next step. The intuition here is, what if there is only one way for a click to not reach the malicious app? So the idea is, if the click reaches the malicious app in a way or another, we know exactly where it clicked. But if there is only one hole and there is only one way that the click does not reach the user, the malicious app, then we can use this flag watch outside touch to understand, hey, the user clicked there. Even if we don't know the coordinates, then we should be able to infer the user clicked there. And let's check this kind of a diagram. Let's say that the attacker wants to convince the user to click on this target button. So the trick is the following. We basically create a bunch of overlays so that the click does not go through, so they're all clickable. And then we create another overlay here in a way that the click actually goes through. And now if the attacker, the user clicks here, well, the click landed on the application. So we're gonna see the coordinates. If he clicks there, the same. But if he clicks there, bam, 0, 0. So if you know that if you get 0, 0, you know somehow that either the user clicked on the corner, which is not very likely, or the user actually clicked in the hole, which is where you want to click. And you can use this information to basically reshuffle your overlays and simulate that, tries to push the user to click on maybe button number 2 that you want for your multi-stage attack. So in this way, we basically know where the user clicked. We know when the user clicked on the target button, and we know when we need to transition to the next step. And again, this stuff actually works. And the idea is that it was possible to mix this context-aware click checking with this context hiding in a way that basically these two attacks were enough to lure the user to enable this CBD service. Basically, from the settings up, it was possible to convince the user to click on this OK button to enable this at the beginning, and then to click on the OK button. I have a video later, but the idea is that, even if we need to convince the user to click here and then here and then here, it's not that complicated, and it's actually possible, okay? And this stuff was quite powerful because now from an app installed on the system, you could create these overlays, and you can somehow, stealing 2 or 3 clicks, you can convince the user to enable a CBD service. And after you have a CBD service, then it's really game over, as I'm going to show you next. Okay. For this study, we actually did a user study. So we recruited 20 students, or no, it was 20 users, human subjects, as they call them, at the university. And they all fell for this. So we gave them a phone with this malicious app. We asked them to play around, and somehow everybody was fooled. Okay. So this stuff was quite practical. And again, some notes about this CBD service. This is the second permission I want to talk about. It's a mechanism for apps to assist users with disabilities. So if you have this CBD service, the idea is that you want to assist the users with disability. And so you have a lot of very powerful capabilities, and you are notified for each UI event, and you can also inject UI events, like such as clicks or putting automatically things there in any widget. And one of the use case, for example, is, I want to be able to read something, the text, and then I would read it out loud for people that have problems in seeing things, okay? It's very powerful, so there are several security mechanisms to avoid abuse, but as it turns out, these mechanisms were not enough. This permission is actually used by several of many top applications. The interesting part for us was that none of these were actually using this permission to assist people with disabilities. So they were using this permission as a trick to do weird stuff, like automatically filling passwords, or blocking a malicious application, or blocking some apps, if you have installed an app locker, and things like this, okay? So that was quite interesting. So again, there are some security mechanisms to prevent abuse, but basically what we found out is that there are several design shortcomings for this CBD service. The idea is that we found out that all UI objects are considered non-security sensitive. So in a sense that, as I mentioned in the past, you read things from every text widget, for example, but if it's security sensitive, then this read will not work. For example, if you have a user password, then you are not able to get text on this user password, you're not going to be able to read it. But it turns out that, sure, they're protecting user password, but what about everything else? And turns out that they were protecting user password, but everything else was not protected, and by default everything was non-security sensitive. And so, one of the main rule in security usually is that security should be the rule, not the exception. And it turns out in this case that this was not followed. And we found out, for example, that sure, the password is protected, but the buttons of the keyboard app are treated as normal widgets. So whenever the user will click on a key, we will get a notification, hey, the user clicked on the button R, and so forth. And so we will be able to recover the password. We'd also found out that widgets like this would be treated as normal or non-security sensitive. So basically, our app will be notified for any new two-factor authentication token. If there is an update, we're going to know it. And the most beautiful thing that I ever found was that even the buttons on the keypad of your, when you need to unlock the phone, were actually considered non-security sensitive. And the cool part is that this tab would also work when you lock the phone. Basically, we have our app in the background. You lock the phone. So great. Now you click on the one. Well, we are going to receive that you clicked on the one. Okay. So what you could do here is to, your app in the background could steal the PIN. So we know your PIN now. And the cool part is that you can inject the PIN and unlock the phone. So if you are an app in the background, basically what you would do is to steal the PIN, and then somehow you can automatically inject the PIN on the phone with the CBD service. And again, you can do this even if the phone is locked and even if your app is in background. And what we found out is that this would also work while keeping the screen off. So we could basically unlock the device, do whatever we want to do. Again, remember, we can automatically inject key events around and basically lock the phone again. Okay. And the user, even if the phone is in front of the user will not suspect anything. And now I have a video that somehow shows the user study we did. So somehow you get an idea about how the attack actually worked. So let's get to it. So basically in this user study, basically we did this click checking attack where we somehow lured the user to install to enable a CBD service. And so to trick the user in doing so, of course, we didn't tell the user there was a study. So we tried to do this attack, and then we asked the user whether he noticed something weird. So in this study, we somehow said, there is a tutorial that will teach you how to be a nice guy. And then once you're ready, please press on the start tutorial. So the user will do start tutorial. And then we will tell the user, in this tutorial, humans will be represented as a green droid as below. Okay, so press next once you're ready, and the user would press next. And then we'll tell the user, okay, you're ready for the main part, and we're going to show you a video, and press OK when you're ready and enjoy the video. And so at this point, the user would press OK, and he would and the video will start. Press OK. At this point, there is a video, and at this point, the attack is already over. So what we've seen was enough to enable the CBD service, and the user, of course, didn't notice anything. And then, it was a nice video, at which point, bam, the attack is over. The user did not see anything, but in the background, what happened is that we stole a malicious app. We enable all the permissions. We enable device admin, and we covered our tracks. We eliminated the recents and things like this. Okay, so sorry. Now I want to show you what actually happened behind the scene. So I'm gonna do the same attack, but I'm gonna have the overlays that are semi-transparent, so you know what was happening in the background. So the first button was a start tutorial. This was basically selecting our app in the accessibility service menu. Once you click on this one, we'll click on the next. The next was actually saying, yes, please activate this. And the final OK was actually the OK button of the accessibility service, okay? And once the user clicked on the OK button, and as you see, sorry. If you see this point, basically it's all covered except the OK button. And this is done to bypass the obscure flag security mechanism. So there is technically no overlay on top of the OK button, and that's why we were able to pull this attack off, okay? And after this, what we would do was to automatically install a malicious app called Google Parental Control, and then we set up device admin, and then we go to permissions, we enable all the permissions, and then since we are pros, we click on recent, we swipe everything off, and we show what we want to show to the user. Bam. So at this point, the app is already installed, is already started, all permissions are there, and good luck finding it. Okay, so that was very cool attack. There was another version, another variant of the attack, just to show what the capabilities would be, and this would be in the terms of ransomware. So the idea is that we will steal the pin with the previous attack, and then what we could do is to keep your eyes out because it's very fast. Basically, we would change the pin, change the message so that we will say, we blocked your phone. Please give me money and so forth, and then we would reboot the phone. So we insert the real pin, we change it to our custom one, and then we change the message and we reboot the phone, and the user is basically locked down of his own phone. Okay, again, that's just an example, but the point is, if you get access to a CBD service, then it's really game over, and you should consider your phone as fully compromised because you can really click around. And again, this attack doesn't bypass any low-level security mechanism. There is no exploit in terms of memory corruption. This is a completely different dimension, and it's very powerful. All right, so moving on, there is another attack that has been one of my favorite, and I call this invisible grid attack. This attack can record all the keystrokes, so I can know exactly what you're typing, and it only relies on this drone top permission. So now we understood that if you have this CBD service, then you really win. But again, this attack now is only using this drone top permission, and then it's let's see what it is. It's not technically a clickjacking, and the beautiful part about this attack is that it works by abusing the obscure flag security mechanism. Okay, so how does the attack work? So let's say this is a picture of the phone laid down. The attacker would do the following. It would basically draw a number of overlays. For simplicity, here I show 4, but you would draw an overlay on top of each key on your keyboard or wherever you want to steal user activity. In this case, again, 4. And the goal of the attacker is to understand where the user clicked, okay? So on which of these 4 parts the user clicked. If you can do this, then you can generalize this to many other overlays. So these overlays are drawn in the following way. They're drawn invisible. So I draw the overlays, but the user does not see them. I draw them in a way that clicks pass through. So if you click on one of them, the actual click reaches the bottom of it, reaches the target application. And then I use this flag watch outside touch, which means that wherever I click, each of these overlay is receiving a motion event. Why? Well, because since I create them in a click pass-through way, none of these click actually reaches the malicious application. Every click reaches the application on the bottom, which technically means that the user is clicked outside these overlays. And that's where this flag watch outside touch kicks in. And that's why each overlay is going to receive a motion event, okay? So again, the goal of the attacker is to understand where did the user click, and what I found out is that the obscure flag is actually set accordingly. What does it mean? Well, it turns out the obscure flag was set in the following way. Let's say that we click on overlay number 1. What the framework would do would be to calculate the impact point of the let's say, or what was the height of the overlay that is first reached by the click, and then it would check this one to say, in terms of overlay 1, is there something above me, or is there something above me? Well, the answer is no. Okay, in this way the click is actually at my level, but the impact point is not above me. And for number 2 it would be the same, right? And for number 3 the same, for number 4 the same. The impact point is always below number 2, number 3, number 4. So for all these guys, the answer would be there is a motion event and the obscure flag is not set. However, if you click on number 2, what happens is there the impact point is actually higher than the overlay number 1. So for motion event delivered to overlay number 1, you're going to see not the obscured, because again the impact point is higher. But for number 2, number 3, number 4, you're going to see, okay, the obscure flag is not set. And I guess now you see the trick. Depending on where you click, number 3 or number 4, you're always going to receive 4 motion events. No matter where you click, you're always going to receive 4 motion events. But the pattern of obscure flag is different. So again, if you click on number 1, you're going to see 4 non-obscured. If you click on number 4, you're going to see obscure, 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 non-obscure. And then basically you can follow these patterns to infer where the user clicked. Okay. So this was beautiful because basically we use the security mechanism, which is the obscure flag, as a side channel to know where the user clicked. And again, the attacker can use these patterns to infer where the user clicked. And again, the irony of using this security mechanism, we showed that it's easy to bypass it. And now we also showed that not only is it easy to bypass it, but it's easy to abuse it. It was very entertaining. And so the proof of concept that we had for this attack was that, instead of drawing 4 overlays, then you would draw many more overlays. And we were able to track exactly where the user would click. And of course, during a real attack, these overlays will be drawn completely invisible. This is shown in this way so that you could see how these overlays will be distributed. But I guess you get an idea. Cool. Another attack that we developed for this paper was an improvement over traditional phishing. So in traditional phishing, what happens is the following. There is an app that shows that, that claims to be Facebook. And, or maybe, the user clicks on the real Facebook. And then at some point, a malicious app pops up and fakes to be Facebook. So the user would interact with this Facebook, fake Facebook version, who put username and password, click login. But then, if the Facebook app was not already logged in, then it's a bit weird, right? Because basically you're not logging the user for real. So the user would actually be still logged out, and the user is confused, like, didn't I click on login? Now, usually this is not the end of the world, because maybe Facebook is already logged in, so you don't notice this, or maybe you thought you put the wrong password. So it's not that this is the end of the world, but we try to understand whether we could do more than this. So somehow we were able to combine this overlays attack with accessibility service in a way to do some kind of a version of phishing that we called stealth phishing. This is the way it works. Somehow we draw overlays on top of this username, password, and login button. The idea is that, again, the user would interact with our username, password, and login button. But the trick is that once the user does this, we would use accessibility service to take the real username and password, put them in the real Facebook app, and click login automatically, at which point the user will find itself completely logged in. So somehow we do some kind of a man in the middle in the UI. We steal the information, and then we use accessibility service to inject this information to the real app. We click automatically on the link on the login, and the user is in. Okay. So we call this UI in the middle, but fancy name, but you get the point. So that was a big overview about some of the attacks that I did some research on in the past. It was quite entertaining. And one question is, are these attacks fixed? So it depends. This invisible grid attack, yes, it's fixed. I think the fix was that now they do not propagate this obscure flag for this outside touch event, and so this prevents us to use this obscure flag as a side channel. What about this clickjacking to accessibility service? This is also fixed. In the new version of Android, whenever you go to a settings app or to an important part of the settings app, all overlays are somehow disabled. So, even if you draw something, if you go to accessibility service menu, then everything disappears. And so the user cannot be fooled anymore. For what concerns this accessibility service that can do more stuff than expected, this was not fixed, and I think it's not fixed as of now. So this was that doesn't work as intended. I told you the story of where there was a documentation saying you shouldn't be able to do something. Then I found a way to do something, and then instead of patching it, they updated the documentation. So they just removed the warning. So this is not fixed. But there was another important point, which is, what about clickjacking in general? Is clickjacking a solved problem in Android? And it turns out the answer is no. Okay, so clickjacking is still kind of widespread. Not in terms of actual attack. It's not that there are many apps using this trick, but in terms of potential, then yes, there are. The vulnerability is still there. And I need to confess, I did not try this on the latest version, but I tried it last year, for example, and I would be ready to bet that this stuff still works. We were able to do clickjacking attacks on the Play Store. Basically, we could hijack and you could fake. We can create overlay, create a Play Store, and then once the user click, the click actually goes on the install. Gmail, where basically, we with the intent we open Gmail with the to and the subject and the message already pre-filled. And so if we convince the user to click on the send, then we will send a ridiculous email around. And we would also work with the Google Authenticator. So if you do a long click on one of these, you would get the information copied in the clipboard. Or Twitter, Facebook, liking, retweet, follow, and stuff like this. It works. Google Drive, if you long click on something, you're gonna share the folder or the document by link, and the link is gonna be copied in a clipboard. So again, the attacker wins. Signal, WhatsApp. So the idea here was to export something to the SD card, for example. In Signal, I think they fixed it in a way that if you now export something to SD card, it's actually encrypted, and they show you the encryption key on the UI. So unless the attacker also has accessibility service, in which case you could just read from Signal messages, you cannot read the encryption key, which means that sure, you can export the database encrypted to the SD card, but again, it's encrypted, you cannot read it. For WhatsApp, it was still working. Again, I don't know, maybe they fixed it in the latest version. But again, just to give you an idea, this stuff is still widespread. And the idea is that, for this accessibility service or for these permissions, they fix it by deleting all overlays, but they really cannot give this the potential to delete all overlays to all these third-party apps, okay? Because it would be very powerful, and then you can create other problems. So basically, you have these third-party apps, including apps from Google itself, that are still vulnerable. And again, to my knowledge, this is not fixed. And on this topic, basically, the first paper is something about all these attacks. The second paper is about a paper with the student from, again, a couple of years ago, where we first of all, we explore that yes, this stuff is still, you can still do clickjacking, and then we try to find a solution for it. It's kind of a, it relies on a modification of the Android framework, so it's not really, you install this and then you're safe. It will require some complex modification to the framework, so we don't know if it's going to happen or not. Anyway, the trick was somehow to understand whether there is what kind of overlays they are on top. Are like kind of semi-transparent, so they're okay, or they are somehow obscuring important parts. So we try to build on top of this idea. I want to conclude with a couple of open problems in mobile UIs, mobile UIs and user interfaces from the security standpoints. And conceptually, what's the problem with these attacks, with this phishing and click checking? Well, one problem is to answer the following question: how can I know that I'm interacting with a specific app? I see something, it looks like Facebook. How can I know if it's Facebook? Okay, how can I know this? It's not possible. So, it is very tricky to get this right. Or how can the app know that the user intentionally and knowingly click on button X? So, for example, let's say that you are the Facebook app and let's say the user clicks on share. How do you know that the user really wanted to press on the share button and it was not a click checking attack? And screw Facebook, right? But what about medical devices? So in the future, the idea is that these telephones and mobile phones, we're going to be able to control sensitive devices such as medical devices. They're going to be able to say, please inject another dose of insulin, for example. And a click in this case that is not, that the user didn't want to click on could be very dangerous. The other side of the coin is, how can I know that my click has been really received? Again, take the medical device as an example. Let's say that you need to say, yes, please give me this dose. But let's say that, you click on it, but the click was stolen by a malicious app. Maybe there was an overlay, the overlay captured the click and the click was not propagated to the medical device. Even the missing click could create problems because you rely on this dose to be injected, but it is not injected, and maybe now you have problems. Okay, so if you don't have the guarantee that your click has been sent to the correct application, has been processed, then you have a potential for denial of service. Again, depending on the situation, this could be life-threatening. In general, how can I know that the user interface content is trusted? How can I know that what I'm seeing is actually being delivered by the app that I think that is delivering it? And again, if you have something like, a mobile or digital identification system like driving licenses, then, sure, I show you my driving license, but how can I know that it's not being tampered with? How do I know that it's not, being photoshopped? So it's quite complicated. And, on this topic, there are some progress, and these progress are actually very exciting. And one of the latest APIs on this topic is called Android Protected Confirmation. And it's one of the big first steps towards a really trusted UI. And somehow it shows a system-generated pop-up asking for user confirmation. So whenever there is a very sensitive question you need to answer the user, the idea is that instead of just asking the user, which is vulnerable to click checking, you would go with this Android Protected Confirmation. So this system will show you a pop-up, and this pop-up doesn't come from the app, and there is no potential for doing click checking there. How does it work? Well, let's check the security features. First of all, this UI with this pop-up is shown by Trustzone. So and rendered by Trustzone. So there is a direct path from Trustzone to the actual UI part. So even if you're root, you can really tamper with this. The other thing is, sure, but how do I know that this UI comes from Trustzone? Well, the trick is that Trustzone is also used to generate an attestation code via cryptography that somehow encodes that the user has clicked on OK and the message was XYZ. Let me rephrase this because it's not trivial. So somehow there is a UI message that is shown by Trustzone, and then the user clicks OK, and then somehow Trustzone registers OK, the user clicked OK, and Trustzone takes the OK, let's say, and takes the message that was shown to the user, and somehow takes this and creates an attestation token starting from this message. Okay. So somehow this attestation code encodes the fact that the user has clicked OK, the message was XYZ, so the user was well informed about this, and the attestation code shows that, hey, this is really Trustzone generating this signature. Okay, and the idea is that you take this attestation code, you can send it off the network backend, And the network backend can verify that yes, this was an okay by user and it was for real, and the user has seen this message, and this was done by Trison, so nobody could jump on top of it doing clicking. So somehow there is high assurance that this this OK button was actually clicked by the user and the user was well informed. Okay, so there is a high confidence, and that's about it. There is actually, I think, a more recent API that is more about this, new system for this, driving license or kind of identification. And I guess the idea there is that they're gonna somehow use the phone to show you the driving license, but there is also some kind of a attestation that shows that this picture actually comes from Trison. And the idea, I guess, there is that maybe the government has access to this part, and it can set up, it can basically, it can produce this, digital version of your driving license, and it's somehow signed by some kind of a trusted authority, and then maybe with through some attestation token, you can show to an officer that this view was not Photoshop, it was actually the real one, and is currently generated by Trust. Okay, so this part is still, let's say, in evolution. It's quite exciting, and I'm looking forward to see what the Android team does on this topic. Okay, so that's all I had to say about UI security. It's a topic that I had fun with. I think it's still, there are still some interesting stuff to play with. I hope you also enjoyed a bit. Please do not hesitate to send me emails, ask me stuff, ping me wherever you want. I'm happy, of course, to help out solving any doubts. Okay, so thanks a lot, and I'll see you next time. Ciao.